Hello, welcome to CSE 351, Introduction to Data Science. Today's topic is about K-means algorithm. So far we talked about supervised learning models in machine learning, in which we have some label data, we have some input and output, and the goal was to design a function by which we can predict the output for a given input. So unsupervised learning models, we have access to feature space. However, we don't have any label for our data. There's no output. So we have no idea what are these feature vectors belongs to. So if they're coming from one distribution, from two distributions, or how they are structured. So in general, unsupervised learning is more difficult and challenging than supervised learning models. So in unsupervised learning, we would like to basically partition or cluster our data and then see if there is some insight or some information in each cluster. So basically the general belief is that the data we have collected or samples we have are from multiple distributions. So can we predict or assign each sample to a corresponding distribution or to a corresponding partition or cluster? And then when we cluster our data, is there any meaning for each cluster? So we can do clustering for any sort of data sets, but we wanted to also find that each cluster represents something, right? So for instance, if you have access to genomic data of some group of patients, and then you cluster this data, and then we wanted to see if each cluster basically represent one type of disease or a sub-disease. So it's important to note when we do clustering, this clustering should be meaningful. Otherwise, we only do clustering based on some mathematical formula, and there is no intuition or meaning behind this clustering. So clustering methods. Clustering methods in general are classified into two groups: partition clustering and hierarchical clustering. So hierarchical clustering is a bottom-up approach. So we consider all samples as one cluster, and then we try to merge samples close to each other and then continue this merging based on some similarity measure until all samples belong to one group. So if you see here, we have hierarchical clustering. This is one example of hierarchical clustering. When we have in here, let's say, different letters, we first consider each letter as a cluster, and then we try to merge these clusters based on some similarity. For instance, in here, A is closer to B, so we first merge these two clusters to form a new cluster, and then we merge these three letters which are close to each other based on some criterion, and then we continue this merge when we have all letters. So in here I have A and B, in here I have C, in here I have E and F, in here I have D, E and F, and in here I have C, D, E and F. So as you see, this is called hierarchical clustering. And the way we visualize the hierarchical clustering is using a graph. It's called dendrogram. But hierarchical clustering, we will have another video lecture to talk about hierarchical clustering. But in practice, for big data, we usually don't use hierarchical clustering because it's very complicated, and also visually it's very hard to find clusters in data. When you have the data more than like a 50,000, hierarchical clustering might not be a good method to go. But today's focus is on partitioning clustering, and partition clustering has there are two different methods. The first one is k-means, which is today's topic, and the other one is Gaussian mixture model, which is a probabilistic approach. So also the k-means and Gaussian mixture models sometimes are called the hard clustering and soft clustering. In k-means, basically for each sample we have a hard decision. We say, okay, either this sample belongs to this cluster or not. The decision is binary, 0 or 1. But for Gaussian mixture model, we consider a distribution consisting of a mixture of some Gaussian distribution, and then we assign a probability for each sample belonging to one of these mixtures. So in fact, a sample can be assigned to all clusters but with different probabilities. And but k-means is a hard decision clustering. A sample belongs or not belongs. So for instance, if I wanted to, let's say this is my feature space, and in k-means I'll basically partition this feature space to different partition or cluster, and then I will assign the sample I have to each of these clusters. So let's say this cluster, these samples go to this cluster or partition, these samples go to this partition, these samples go to this partition, and then this sample goes to this partition, and then these samples go to this partition. So as you see, I have all these samples with different colors, 5 colors, then I partition them, the entire feature space. So each sample only belongs to one partition. This sample belongs to this partition and not belongs to partition. But Gaussian mixture models, in a 1D illustration, we basically assign some mixture of Gaussian probability like this, and then if you have a sample, let's say this sample belongs, and then we assign, and in here I have 4 Gaussian mixtures with different means, and then this sample belongs with different probability to each of these mixtures. Okay, so this is a probabilistic approach. We will talk about this one also in another lecture, but we will focus on k-means in here. So k-means. Now we are ready to have a formal definition and also how the pseudocode for k-means works. So suppose that we have n vectors of dimension p. So when it comes to clustering, I have seen many students have problem to visualize how we wanted to cluster vectors. So it's very easy to one-dimensional or two-dimensional data because we can visualize and then we can see the scatter plots, how we cluster the data. But for more than 2-dimension or 3-dimension, when you deal with vectors, it's hard to visualize it. But usually when we deal with the k-means, we are clustering vectors. Okay, so imagine you have n vectors, and then these vectors, each vector has a dimension of p, and we have n vectors, and we would like to partition, we would like to assign each of these samples to a partition. This is called the k-means algorithm. Also, traditionally, k-means algorithm was known as vector quantization. So that was a very popular technique they used for the speech coding. When you wanted to speech encoder, when you wanted to compress the speech signal, they used the technique called vector quantization. But this technique is also basically was another version of k-means. So for k-means algorithm, another important note about k-means is that usually the number of clusters are not known, and this is very important issue for practical application. You are given some data, but we don't know how many clusters are in this data. But for now, let's assume that we know the number of clusters or number of partitions is k. We have k partitions. So we wanted to see. Then when you want to partition the data, when you want to cluster the data, we should have a similarity measure or a distance measure. This is a key in clustering. So when we are comparing two samples, are they belong to the same cluster or not? So therefore we need to devise a similarity measure and also a distance measure. So they are equivalent. So the goal of k-means is if you have a pair or two sample or two vectors, they should belong to the same cluster if the distance between these two vectors is as close as possible. And also two vectors belong to different clusters if the distance between these two vectors is as large as possible. So in here we define a distance measure, and then we denote it by d, and then distance measure. So there are many different distance measures when it comes to clustering, but the most popular distance measure is Euclidean distance, which we discussed in detail in linear algebra and also vector analysis. We use Euclidean distance between two vectors as a distance measure. As you see, if the distance between two vectors is small, that means these two vectors are similar, and if the distance between two vectors is high, this means these vectors are dissimilar to each other. So these are two goals we are following when we wanted to do k-means algorithm. So the idea is now clear what we wanted to do. We have n vectors. We wanted to cluster these vectors into k partition. K is known, and the goal is when we set a group of these vectors to one cluster, the distance between these vectors should be as small as possible, and then if you pick two samples from two different clusters, the distance between two vectors should be as high as possible. So based on these two notions, we now ready to see what steps we need to take to do the k-means algorithm. Here is a visual example about k-means. So as you see on the left, we have clustered a bunch of vectors, n number of vectors, xi, xji, into 16 clusters, right? We have these, each subplot is one cluster. Cluster 1, cluster 2, cluster 3, all the way to cluster 16, okay? And then we plotted in each subplot the member of each cluster. So we wanted to design an algorithm that basically, as you see, all these vectors, they belong to this cluster. They have some similarity, right? They're similar. So, and then we set the number of clusters to 16. Let's say if you have 160 vectors, and then each cluster might have an average 10 or more. So it's not if you cluster 160 vectors to 16 cluster, each cluster has 10 vectors. It's not true. The number of members of each cluster might be different from the others. So in fact, some cluster might be very rare and they only have maybe one or two vectors. So when we have some outliers in our data. What you see on the right is the center of each cluster. So this is also an important concept in k-means the center of each cluster. So the center of each cluster is nothing but the mean of some vectors. So we already talked about how to compute the mean of some vector. So mean of some vectors, if you have, let's say, k vectors, so then you sum up all these vectors element wise. So let's say we have these vectors, and then we divide these vectors by k, by number of vectors. So this is how we compute the mean or center of clusters. We add up all these vectors. For instance, for this example, we add up all these vectors element by element, and then we divide the resulting vector by the scalar, which is equal to number of the vectors. So as you see, these are the center of clusters. These center of clusters are what we use for the further analysis. For instance, I said about the vector quantization or k-means that was used for speech encoders. So if we basically, for small pieces of speech, we, let's say 20 samples, there's one representative for all these member of one cluster, and that is the representative. And also in here, look, the 20 in here is the dimensional vector. So basically p is 20 in here if you refer to the previous slide. So how many samples we have? We have n samples. What's the dimensional feature space is 20. So don't mix up these things. So sometimes I have seen when we have a big matrix and we wanted to do clustering, we should know that either we wanted to do clustering for columns and rows, and which one represents sample, which one represent feature vector. Okay, so that's a visual example of k-means. Now let's see how we can do the k-means. So k-means algorithm, the original one, has basically 5 steps. In the first step, we should know how many clusters we have in this data. So this is something usually we can get the expert opinion, or we have some idea, or we were told to assign k clusters. So k should be identified upfront. And in fact, this is one of the shortcoming of k-means, that we need to know the number of clusters prior. But for now, we decide how many clusters are in this data, and then we need to find initialize the cluster centers. We initialize these cluster centers randomly. So basically, we generate some random vectors, and we assume that these are our cluster. These are the initial center of cluster. So if you have 10 clusters, we generate 10 random vectors. So in fact, we actually generate these vectors. So these vectors generates first randomly. And then in the third step, what do? We do the decide the cluster membership for n samples. So if you have n samples, and then we compare each sample to each of these center of clusters, and we assign that sample to the center to which it is closer based on the similarity measure we are using. And in here, we use the similarity measure based on Euclidean distance. So if, for instance, in this two-dimensional representation, let's say I have assigned these point these 2 points as two random cluster. Okay, these 2 points. Now, if I have these two data, this and this, so I will compare the distance between this point and this center and this center, and then this point is closer to this cluster, then I will assign this point to this cluster, And then also I measure the distance between this point and this center, and this point and this center, and this point is closer to this center, and I will assign it to this cluster. I will assign it to this cluster. So if I call this one cluster 1 and this one cluster 2, the centers, and if this is member, let's say 100, and this is member 120, I will say the sample 120, 102 belongs to cluster 2, and the membership for the sample 100 is cluster 1. So the third step is to assign the membership for each sample by comparing each sample with all centers and find the one which is closest. After we assign the sample, we repeat the process again. So we recompute the center of each cluster. So now we have the membership for each cluster, we compute the centers, and then now we have new centers. And after we find this new center, we go back to step 3 and then repeat the step 3. And now again for each sample, we will find the closest center, and then we assign the membership to each sample based on the new means, and then we update the sample of clusters and repeat this process 3 and 4, back and forth until we found that the membership for each cluster doesn't change at all. At that point we stop. So as you see, the k-means is very simple and a straightforward algorithm. So there are 5 steps. The first step, we define the number of clusters. Second step, we initialize the clusters, randomly initialize the center of clusters, and then we assign the membership for each sample. We recompute the center of each cluster, and then we repeat this process. As you see, this is here is an example that which this dark points shows the center of each cluster, and each color represent a cluster membership. So all these points in here, they belong to this cluster. Okay, so these are some uniform random data, generated data, and then we just do the clustering. Know that, as I said, for any type of data we can do clustering, but there should be some meaning about this clustering. Otherwise, if we cannot infer some knowledge from this clustering is not useful. So let's also take a look at the pseudocode for k-means. As I said, in here we use C as C vectors as a center of cluster. If we set the number of clusters to k, then we have a k cluster. So this capital K shows the center of clusters. So, and then these are the vectors. Note that these are vector of a dimension p. Each of them is p by 1, right? These are vectors. These are not scalar. So first of all, we initially randomize the centers. So then we choose some random vectors, and then repeat this process, these two processes until the convergence occurs. So at the first step, we assign the membership for each sample, and then in order to assign the membership, how to read this formula. If we compare each sample to the center of each cluster, and we find the cluster to which these sample is closest, and then for the sample jth, we assign this cluster. So for instance, if we say M50 equals to 20, that means the sample 50 belongs to cluster 20. Sample 50 belongs to cluster 20, right? So in here, K is 20 and J is 50, okay? So this process is just finding the membership for each sample based on the current estimate of the center of each cluster. The next step is now we recompute the center of each cluster. So as I said, when you wanted to find the center of each cluster based on the members, we take the average of these vectors. So this formula basically is nothing but computing the center of each cluster. So then we basically do a sum. So this one basically, what is this sum means? This sum means, let's say, I give you an example in here. Let's say I have two clusters, and then these samples belongs to this cluster, 3 samples, and 2 samples belong to this cluster. 2 samples belong to this cluster. Okay, so I just labeled them 1, 2, 3, 4, 5. So if I want to compute now C, let's call this one cluster number 1, and this one cluster number 2. If I want to find the center of cluster number 1, then what I do, I basically, how many samples I have in cluster 1 is 3, so the denominator is 3. So this is basically, this one is a function saying that if these sample j's belong to cluster 1, this is equal 1, otherwise is 0. And this for all samples, we find the membership. If the membership is equal to k, then this is equal to 1. Otherwise, this is equal to 0. Then 0 times vector, and this is a vector. So in here, what we do, this cluster has 3 samples. So if I wanted to run this sum on all samples, then I have vector x1 plus x2 plus x3 plus x4 plus x5. These are vectors, okay? But we know that in here, samples 4 and 5 belong to other clusters, so therefore these are multiplied by 0, and the others, these are multiplied by 1. 1 times this, 1 times this, and 1 times this. This is basically what this sum means. And then we sum up these 3 vectors, so then C1 is equal to x1 plus x2 plus x3 divided by number of samples in this cluster. This is how we compute the centers. And then we repeat this process. Membership assignments, recompute it in center until we don't see any change in membership. And then at that point we stop. Also note that there is this method calls k-means with random initialization. Sometimes this method is very slow. Another way to do this is it is called binary splitting. So basically we first consider the average of all sample as one cluster, split it to 2, and then repeat this process to get desired number of clusters. The problem with this method is number of clusters should be a power of 2, 2, 4, 8, 16, and so on and so forth. Another way, if you wanted to have a robust k-means method, it is suggested to run the k-means method with different initialization to find a very robust clustering. And also we need to, as a performance evaluation, what we can do, we can also report the distance of the samples belonging to one cluster to the center for all clusters, and then report the average of this distance as a number to show how this clustering performing. But as I said, mostly because we have no idea about the number of clusters, what we need to do is, if we found one cluster have some attributes, some features related to the phenomena we are studying, that clustering is a good clustering. Otherwise, even though you might find a very good numbers, but if there is no explanation about this clustering, then this clustering is probably useless. So far we assume that the number of clusters are known, but in practice, as I said, for many cases we don't know the number of clusters. How to specify the optimal number of clusters in k-means? This is not, it's a very simple method. So what we do basically, we start by assuming that this data, the optimal number of this clusters data is 1, 2, 3, 4, and then repeat to have the kth clusters. And for each clustering, we compute the average of within cluster distance. So that means for all samples belonging to one cluster, we compute the average of distance, and then we take this average for all clusters. This is a criterion that shows that how the clustering is doing. So this shows that what we wanted to minimize the within cluster membership, and also we wanted to maximize the between cluster membership. So that's a number that reflects that goal. So then we do the clustering and we measure this criterion, and then we have a plot. In this plot, on x-axis we have the number of clusters. As you see in here, we have 2 clusters, 4 clusters, 6 clusters, 8 and 10, and then on y-axis we have this error of clustering. Let's call it the error of clustering. So as we increase the number of clusters, it is obvious that the clustering error decreases. But if you increase the number of clusters, you will see always an elbow curve in showing the error of a clustering with respect to number of clusters. So there is a point beyond which, if you increase the number of clusters, you know that the error doesn't change that much. So then we'll decide the elbow of this curve is where there are the optimum number of clusters, and we stop there. As I said, it's obvious let's say if you have 100 points, and if I increase the number of clusters to 100, the clustering error would be 0, because each sample would be one center, and the distance to the center for each cluster is 0. But this is not an optimal way, so we should find somewhere, it's in a convention that we consider the elbow of this cluster as elbow of this curve as the optimal number of clusters. So in here, if I just draw a vertical line, this line just crosses this number of clusters, 3. So I would say the optimal number of clusters for this example is 3. So for real examples, sometimes let's say you have 10 billion samples, right? And then should I start from 1 and go all the way to 1 million? Should I run the k-means algorithm 1 million times? In fact, if you are getting expert D, you will guess and based on the study undertaking, you can kind of guess the number of clusters should be, let's say maybe for 1 billion samples, I can try a different beans. I can start by 1,000, go to 1 million to see how the clustering works, and then I would come to a range, and then granule that range to smaller beans. So, but the idea is try different case and then find the optimal one. But the way to go is using elbow algorithm. As I said, this is one of the shortcomings of k-means, and then how to combat with this problem, how to mitigate the effect, is using the elbow method, which is frequently used in k-means algorithm. So this is the method how to find the number of clusters in k-means. And finally, if you wanted to implement and use the k-means algorithm, there are a number of libraries when you can use the k-mean. You can also simply by writing 2-3 lines of code, you can implement k-means, but it is efficiently implemented in scikit-learn. Here is an example, a toy example, again on iris data. So as you see, you need to import the cluster this library contains the k-means algorithm, and also we in here we do, in this example we download the data set. From the data set we get the load iris. So these are some toy examples that are already imported to the scikit-learn library for some demos. So we get this data. These data, they have some features. So basically this is x jth vectors, and we have also labels. We know that each flower belongs to one group. These are three groups. So we know up front for this example that the iris flowers belong to three categories. We wanted to now investigate that, saying that if, let's say, we don't have the labels for this flower, if we cluster them, then can we distinguish between this cluster? Each sub category of flowers would be into one cluster. As you see in here, what we do from the cluster library, we make an object for k-means. So this is the function you need to use, and then this function has several input arguments. The most important one is assign the number of clusters. So in here we set the number of clusters to 3, and then we create an object. Now we need to do the training. We need to do the k-means. Then we call the method feed, and then feed our data, the x's I, x's j. So these are the input vectors, and then we do the k-means. And then here we print the label. So this is the membership. So we play the membership to which cluster each sample belongs, and also we print the output labels with different colors. As you see here, we have 3 distinguished clusters, as you see, and also each color shows the true label for each cluster. So as you see that for this example, let's say we don't know the labels for these flowers. If we do the clustering, then we can obviously see 3 clusters flowers. So this is what ideally we wanted to do, but in practice we don't have labels. We basically do the clustering, and then we look at the data, and then we study each cluster and find, okay, this cluster has some attribute which is different from the others. How much other insight, how much more information we can get from these clusters which distinguish them from the others. This is extremely also important in some medical applications. When we study the patients, we have no idea upfront how these patients are, to which subtype they belong, but based on, because we don't have any label, based on the clustering, we should do the study. So as I said, the unsupervised learning in field of data science and machine learning is a very challenging topic these days, and then finding good cluster with data can help us to gain lots of insight and knowledge about our data. So this was the end of this lecture. So basically we study one technique in unsupervised learning which is very popular. It's called k-means, which is a partitioning clustering technique. And in other videos we also talk about Gaussian mixture models and hierarchical clustering, that they are other 2 different methods. Gaussian mixture models are very powerful probabilistic approach in order to assign a sample population to different distribution and assign some probability. And also the hierarchical clusterings are a very good way to give us some insight about data when we don't know the number of clusters. They show us how the data are merged together to form a new cluster. I wish you all a good day or night, and then I'll see you in next video.